Hello there ladies and gentlemen, this is Norris Salam for Schrodinger. In this tutorial we are going to cover the Scaffold Decomposition application from within Canvas. So this application simply refers to a process of easily identifying the common structural scaffolds from a collection of molecules. Now this is useful in that it can allow you to achieve three particular goals. First, you can identify scaffolds with a bias towards a specific property. A good example would be identifying the common structural scaffold among molecules with high activity. Secondly, you can isolate structures containing a privileged core. And third, you can perform R-group analysis around that core. Okay, so let's get started. On screen we have a dataset of 71 CDK2 inhibitors with 10 columns containing properties. In particular, activity data represented here by PIC50. Now the first thing one often does when they have a selection of properties is to examine the distribution of those values in a chart. So let's quickly take a look at a histogram by heading up to Chart, then Histogram. Okay, so PIC50 is already the first property displayed, but if you wanted to display other properties, you'd select it from the drop-down menu. So a worthy goal when viewing a histogram of activity alongside the chemical structure shown on the left would be to determine whether there was anything common among the potent compounds, like those with PIC50s above 8. In other words, the question to ask would be, are there any structural features or scaffolds that are common amongst these potent compounds? And one way to answer that is via the Scaffold Decomposition application. So let's head up to Applications, Scaffold Decomposition. Now the dataset we are working with are the visible rows, and we'll keep the default result name. When finding structures that contain a scaffold, you can choose to match scaffolds to a fused ring system in a structure that contains the scaffold. This is called an embedded match, and you can allow them by selecting Allow Embedded Matches. So for example, if the list of scaffolds contain imidazole and benzimidazole, when embedded matches are allowed, then the structures that contain the benzimidazole will be included in the structures that contain the imidazole. Identifying embedded matches takes substantially more time than not doing so, so we'll leave it unchecked in this example. When ready, click Start. After the job finishes, you can view the results by right-clicking on the job and choosing View. Here you can see the 2D structures of the scaffolds in a table. They are classified by the number of rings in each scaffold or by the number of ring systems. The property we're interested in was the PIC50, so let's choose that from the menu. You'll notice that below each structure is a stick spectrum representing the property distribution, in this case the PIC50 distribution. So let me bring up the legend to explain this in greater detail. Vertical bars indicate a structure, or more specifically a structure with the property containing the scaffold shown. The average property value is marked by the triangle, and the region outside one standard deviation from the average is coloured if it contains the vertical lines. Let's look at our example. It's pretty clear that all the compounds contain a benzene ring, which is why there are a lot of sticks representing all of the compounds in this spectrum. But if we look over here at this spectrum, we can see that there are more structures containing this 3-ring scaffold with PIC50s greater than average, including a few that are significantly potent. Contrast this to the left, where most of the structures have PIC50s lower than average. And straight away I can tell that this difference is likely attributed to the presence or absence of the double bond. So clearly, at this point, we can already answer part of our original question and say that this particular 3-ring scaffold is common among the compounds with high activity. From here, we can dive deeper and examine the compounds that contain this scaffold by first selecting it and then clicking on Show Source Structure. This brings up a table with the structures containing just that scaffold of interest, but the great thing here is that it also shows the stick spectrum, so you can see if there are any outliers worth investigating. So, for example, I can immediately see that there is something interesting about this structure, given that it has low activity despite containing the potent scaffold. Perhaps other R group features attached to this scaffold are countering its beneficial effects. And that leads us on to the final step. You can either export all of the structures here, or you can go further analyze the structure by clicking here. That'll bring you to the R group analysis application where you can analyze the various R groups. So in summary, if your end goal is to identify scaffolds with a bias towards a specific property, such as high activity, or to isolate structures containing a privileged core from where you can go off and perform R group analysis around that core, then I strongly recommend you try out the Scaffold Decomposition application from within Canvas. One useful task I didn't mention is that you can also use Scaffold Decomposition to verify the diversity of libraries. So for example, counting the number of unique scaffolds produced by Scaffold Decomposition from 2 libraries should provide you with some indication as to how diverse the libraries are. In other words, the library with the most unique scaffolds would represent a library that is more structurally diverse than the other. For more information on Scaffold Decomposition, please refer to the Canvas user manual or contact help@schrodinger.com. If you are new to the Schrodinger suite and would like to gain access to Scaffold Decomposition and many other useful cheminformatic features from Canvas, please contact info@schrodinger.com.